Thank you all very much. It's an honor and a pleasure to be here tonight to be able to present the Asteroid Redirect Mission to you. I'm going to give you an overview and also emphasize its importance for NASA's journey to Mars. So NASA has a plan to incrementally step out into the solar system, and ARM is a focal point of that plan right now. As Bob said, I'm serving as the mission investigator on the ARM mission. And it is not a science mission. So let me start off and say it is a capability demonstration mission. It's sponsored out of the Human Exploration and Operations Mission Director at HEOMD. But it has, anytime you go out into the solar system and you start exploring, there is science. But it's actually bigger than that. We have a planetary defense component, a in situ resources, an asteroidal resources component, and as well as the human mission and the science that we can do on the mission. So first I'm going to start off by, and just to confirm, I do have 30 minutes, Bob? Okay, yes. Okay? A little bit? Yeah, 30 okay.
Minutes. Rest of the schedule's moving to the right.
And I don't know if we can bring the lights down by any chance up front? Or,
it basically goes from this to all.
Okay. I don't know if off might work, actually. Are you all comfortable in the dark out here? Oh, that is true. Thank you so much. Sorry about that. Okay. I hope you guys can see this. I'll try to point it out with the laser pointer, and point out this kind of font's kind of hard to read. But this is a depiction, and some of you may have seen this, of NASA's Journey to Mars, our program, and it basically is a three-phase proposal. Right now, we are kind of in an Earth-reliant phase where we've been on space station for quite a while yet. I started off working on space station, doing the conceptual designs and the redesigns for the International Space Station and its predecessor. But we're sitting here in low Earth orbit in the International Space Station, and it's been a long time since we've been out into deep space. A lot of the expertise of Apollo we have a lot of knowledge from those days, but the expertise has retired. What we would like to do is step out incrementally, kind of getting your sea legs a little bit before venturing out into the open ocean. And we have a concept called the proving ground. So when we have missions in low Earth orbit, we can return in a matter of hours. And obviously, as everybody in this audience knows, Journey to Mars with current propulsion systems is a multi-year, in all likelihood, a multi-year endeavor. We can increase the propulsive capabilities, we can decrease that, but we're certainly not at the point where we can get there in hours. We don't have warp drive yet. In the proving ground, you can return in the matter of days, maybe a week, depending on where you go. And this proving ground is the area around the moon, we call it cislunar space, but it's basically an orbital training ground for the astronauts and the robotic systems that we're going to need to venture further out. And as we move out to the red planet, the technologies and the capabilities that we develop with the ARM mission will provide the basis for the operations in the spacecraft that we need on the journey to Mars. One of the possible gateways to the surface is through the Martian moons. And if that route is decided to go upon rather than a direct to the surface on the first mission, the Asteroid Redirect Mission is very applicable to the Martian moons and exploring those, and potentially using the moons as a basis for extracting materials to make a more sustainable Mars mission concept. Yeah, that's a little bit better. Thank you. Is that still good on the lights? Okay. A lot of words on this chart, but these are the strategic principles for sustained exploration, and that is a key aspect to what NASA is trying to do. We want to move out incrementally, as I mentioned, but we want to do so in a sustained manner. And I want to read you all the words. You can read what you want, but if you just highlight on the yellow golden topics here, the plan has to be fiscally realistic. We have a fixed budget. We have certain other missions that we don't want to impinge upon, and we've got to be able to do it within that budget. There's a scientific exploration component. Again, as you explore, there's scientific discovery and knowledge gain, I like to call it, because there's applied engineering and other aspects besides just simply pure science. There's technology pull and push. We have technologies that we know we need to advance, and we can also push missions with other technologies that we can rapidly develop. Gradual buildup of capability. As I mentioned, we want to move in an incremental fashion. Economic opportunity, a key aspect of the journey to Mars and the plans to move out into the solar system is to involve commercial partners in new ways, including the potential for the Asteroid Redirect mission to promote commercial mining enterprises. Architecture openness and resilience, that means basically we want to be able to infuse different infrastructure and actually have it resilient to failure and other issues. Global collaboration and leadership, we want to do this in a way similar to the International Space Station by leveraging our partners throughout the world, and the continuity of human spaceflight, to do it in an uninterrupted manner, that we don't have a hiatus for a long period of time. So this chart kind of shows how we move out from testing on the International Space Station, what we kind of call phase 0, the exploration systems, moving out into cislunar space, which the Asteroid Redirect crewed mission will venture out, and I'll explain the different segments of the Asteroid Redirect mission, but it has a crewed component and a robotic component. So it is really a great example of the synthesis between robotic and human exploration and the interaction. So this is where we're talking about the Asteroid Redirect mission fitting in. And then cislunar validation ends with a 1-year crewed Mars-class shakedown type of a cruise. So before we get to the surface, entry, descent, and landing, other aspects are more difficult. We may end up doing a cruise shakedown, and we may also explore beyond the Earth-Moon system into the Martian system. As I mentioned, we may go to the Martian moons as a first precursor to the surface, but our stated horizon goal at NASA is a Mars human landing mission in phase 4. And you can see the time frame on here. Folks in the back hopefully can see it, but this is the mid-20s that we're talking about. And I'll explain more about the time frame for ARM in a minute. But in the 2030s and out, hopefully not too much past the 2030 mark, we'll be looking at human landing on Mars. So the Asteroid Redirect mission has 3 main segments. There's an identification, and that's where we're using ground-based assets as well as space-based assets to look for targets. And along the way, this has a huge benefit for planetary defense, because as we look for these targets and we're infusing more funds into the detection, not only do we find targets for the Asteroid Redirect mission and commercial mining aspects, but we can also, we increase the catalog of known objects from a planetary defense standpoint in case one day in the future we have to deflect one that's on a collision course with the Earth. The redirect portion of it is the robotic segment that is focused on using solar electric propulsion, high efficiency, high power solar electric propulsion, to return an asteroid boulder back to cislunar space. So we're going to go to a near-Earth asteroid, descend down to the surface in an autonomous mode, because we have multi-minute, maybe 15-minute time delay at some points, and basically land on top of a boulder within about 1.5 feet, about a half a meter accuracy, pick up that boulder and return it off the surface. We also plan to get regolith samples as we touch the surface, and I'll show you a video and explain the robotic operations. But once that boulder's back in cislunar space, we will launch 2 crew members as the current baseline aboard the SLS, the Space Launch System rocket that NASA is developing. They will be aboard the Orion spacecraft and rendezvous with both the boulder and the robotic spacecraft in a stable orbit around the moon. They will explore the boulder, return samples from the boulder, and practice a lot of the operational aspects of deep space docking and rendezvous, extravehicular activity, doing spacewalks, sample containment. This will actually be the first human sample return mission when it happens in over 50 years. So, quick slide on the objectives, just to make sure it's clear what the Asteroid Redirect mission is trying to achieve. First of all, we want to conduct that human exploration mission involving in-space interaction with the asteroid boulder in the mid-2020s, again, providing the systems and operational experience required for human exploration of Mars. Want to demonstrate the advanced solar electric propulsion, and that's critical. I'll have a slide on that in a little bit, enabling the future deep space human and robotic exploration. There's plenty of applications in the robotic sector as well. Enhance, as I mentioned, detection, tracking, and characterization, demonstrate planetary defense techniques that will inform threat mitigation strategies to defend our planet, And again, pursue a target of opportunity that benefits science and partnership interests, expands our knowledge of these small celestial bodies, which are widely varied. Our knowledge is far from complete for asteroids and comets, but also enable the mining of asteroid resources for both commercial and exploration needs. So just a timeline of what we're talking about. Here we've got the identification segment, the detection segment, with enhances to different telescope systems. These are just examples. There's plenty out there. If your favorite telescope's not up there, please don't be offended. We've got a whole network of ground-based as well as space-based assets that we can turn to. We will make a final target selection for the Asteroid Redirect mission about a year before launch. Our current launch readiness date is December of 2021. That being said, we have a reference target that we are designing to that we think is a great target, and I'll talk about that in a second. But if we find an additional target and we get good observations on it, we potentially could select that as an alternate target. The Asteroid Redirect mission will be launched, like I said, in 2021. Spacecraft PDR is in November of 2017 planned, and then delivery of the EP system sometime in the 2020 frame, just a couple milestones for the mission. Takes about 2 years to get out. We'll do the rendezvous characterization and the boulder capture. Then we're going to demonstrate the enhanced gravity tractor planetary defense technique, and I've got a slide, I'll talk a little bit about that. After that's completed, we'll return with the asteroid boulder to the lunar vicinity. And then the last part is the Asteroid Redirect crewed mission segment, which starts off with the exploration flight tests that already occurred here in 2015, and a first uncrewed mission of the Orion spacecraft. And it'll go out past the moon, return, check out all the systems. There's then plans to do at least one crewed mission beyond the moon. Again, these will be orbital missions. We don't have a lander to get down to the surface of the moon. And then finally, in late 2026, once the boulder and the asteroid redirect vehicle are back in lunar vicinity, the crew will be deployed to the asteroid boulder in a stable orbit. We're currently looking at different options for that orbit. And the asteroid redirect mission just entered phase B, so we're still in the preliminary design phase of the mission, but this is when we're going to start to nail down our reference target, our reference trajectory, and the different aspects of the mission. So I'm just going to let you watch this animation, and then I'll talk a little bit about it at the end. I think there's a little bit of music. Okay, so as a fast-paced animation, there's a lot of content in there. I'll going to talk a little bit about it as we go through the rest of the slides. But again, this boulder that we're bringing back, our reference target is 2008 EV5. And you can see it's about a 400-ish meter asteroid. It's kind of a oblate spheroid. It's got an equatorial bulge where it's expected that there are mass has sloughed basically based on its rotational rate down into that area. We have radar data on the target that indicates that there are large boulders that we can see with the resolution of our radar, and based on other asteroid missions and profiles of the size of boulders that we can expect, we expect hundreds of boulders in the size that we can bring back. And our reference mass that we can bring back from 2008 EV5 is 20 tons. That represents a similar mass that you might move around with a solar electric propulsion vehicle in cislunar space, and eventually larger masses as we move out in the solar system. Things like pushing out landers, habitats, and for example, on the surface of Phobos or Deimos, you might land a habitat, which is kind of the inverse of what we're actually doing, lifting the boulder off the surface with the robotic systems that we're developing. One of the important things about 2008 EV5 is that it is a C-type, a carbonaceous type asteroid. The carbon content makes it very dark, and it's not the carbon that we're after, it's the water is the primary interest in terms of the resource that's available. Expected to be about 20% water, but there are other volatiles as well as organic molecules that will provide information about the origins of the solar system, origins of life on Earth. So it's very scientifically interesting, as well as interesting for resource companies that may end up wanting to process that type of material. And most of the asteroidal resource companies that are out there have been focusing as well on the water. Now we can also do in situ manufacturing and create radiation shielding and other aspects from the material. But that's an important part as well as the other aspects of ARM. There are a couple other targets that we could go to, but actually Bennu and 1999 JU3, which has actually been renamed to Ryugu, I can never pronounce the name properly, but Hayabusa 2 is going out there, and OSIRIS-REx just launched a couple weeks ago now on its way to Bennu. We've already visited Itokawa, so 2008 EV5 represents a new object that we haven't gone to. And it actually is the largest, most accessible near-Earth asteroid known currently in the solar system, meaning there are more accessible ones, but they're smaller. And so it is a large carbonaceous asteroid, which the Martian moons may or may not be carbonaceous in nature. They may be asteroids. They may be developed, our origins may come from a different source, but they appear to have striking resemblance to carbonaceous asteroids. So just a quick outline, what you saw in the video. The launch, the outbound cruise, takes a little bit over 2 years, depending on the trajectory we fly. The characterization phase is about 100 days right now. We're looking at options to try to extend our time at the asteroid, but right now we've got a baseline of 100 days. With 50 days of boulder collection operations, that includes the dry runs, what we call. We'll go down to 50 meters above the boulder that we want to select, or that we want to capture that's been selected, and we'll practice that out. We're planning on characterizing 5 sites for a boulder and the landing site around it, and then have 2, a primary and a backup boulder that we'll make attempts to. Of course, it depends on what we find there. We might find a plethora of targets. We might have more than that. And we just have to see once we get there and do the characterization and the mapping. There's also 50 days of margin built into that boulder collection operation. And then once we have that boulder, we'll do the planetary defense demonstration using the enhanced gravity tractor, which I'll talk about just in a minute. We've got the inbound cruise, which takes a little bit longer than the outbound because now your vehicle mass has gone from 10 tons to approximately 30 tons or even more with the 20-ton boulder attached. We then have the crew operations, and then we have a transfer to a long-term stable orbit. We're still doing trades on where exactly the crew will rendezvous, But the final goal is to put it in a distant retrograde orbit that is stable over a long period of time, but is still accessible. So the enhanced gravity tractor, I know this is focused on Mars, but I want to spend just a second because it's an important aspect of the ARM mission is to do planetary defense. And what we're going to do is show a slow push technique that leverages the gravitational attraction of the spacecraft to the parent asteroid, to the target. 2008 EV5 is a hazardous size asteroid, so it's a great target to practice on. We are going to deflect it by a fraction of a millimeter per second. Very small delta V, but discernible that we can measure. For 2008 EV5, there are actually ground-based radar opportunities where we can measure that deflection. We also potentially, if we pick another target, we can stay in orbit and do a radio science experiment and discern the movement with the spacecraft. This is just an example of the crude reference trajectory, which you kind of saw in the video. Outbound time is about 8 days. The return time flight is 11. The time that we stay in in this case, the distant retrograde orbit is 5 days. The crew will do 2 4-hour EVAs by depressing, as you saw in the video, the crew cabin of the Orion and then venturing out. We are looking at options to expand that duration, expand the time that the time available out there, but that's the current baseline. This is just a timeline of the crewed robotic system, or the crewed segment when it rendezvous with the robotic system. The orbit that we're currently looking at is about a 71,000 kilometer lunar distant retrograde orbit. And if I go back, you can kind of see, here's the moon. I forgot to point this out since some folks in the back might not be able to read that very carefully. And this is obviously not to scale to the Earth, but it gives you an idea of the distance of the orbit and the trajectory around the moon. Again, I mentioned there's 2 4-hour EVAs, and one of the key things is that the crew will be able to practice sample containment, which is a critical aspect of anywhere that we venture into the solar system, particularly the Martian system, as we go out and want to return samples. So, focusing back on what are the contributions of ARM to the journey to Mars, one of the first things is the autonomous proximity operations in deep space with the natural body. We have, as you saw in the video, there is a multi-limbed robotic system. We basically have 3 legs, which we call the contact and restraint subsystem. We have 2 robotic arms, and then we have 2 tools, or hands and fingers, based on a microspine technology. So anthropomorphically, you can think about it. You've got 3 legs. We're going to land on top of this boulder. We're going to use those legs, the CRS, to attenuate the landing loads and support the operations while we're on the surface. We're actually going to end up thrusting downward, thrusting upward, creating a force downward to keep us on the surface, while the robotic arms and the microspine grippers attach to the boulder, anchor to it, and then we're going to mechanically push off the surface. The video is real quick, but it takes about 10 minutes to drop down from 50 meters. And we're going to be able to mechanically land and mechanically push off, at least to a point where we can then fire jets safely and reach escape velocity. We might potentially be able to reach escape velocity from 2000 EV5 just mechanically. And the reason for that is to try to minimize any disturbance of dust and other particulates on the surface. The solar electric power is important, and I've talked about that. I'll show a slide here a little bit more on that. The integrated crew robotic vehicle operations in deep space, and again, the astronaut EVA and sample selection and handling is important. This just highlights some of the key technologies and capabilities: the high-efficiency solar arrays, high power, high efficiency, the high power, high throughput electric propulsion. These systems have to last many, many years. If we start using solar electric propulsion as tugboats to push material around the solar system, in particular, if we pre-deploy habitats and landers in the Martian system, they have to function for many, many years. The autonomous deep space proximity operations, and again, EVA and deep space rendezvous. So we've started out in the 1990s with 1 kilowatt SEP systems, and we progressed in the early 2000s up to about 10 kilowatts. We're making the next incremental step to 50 kilowatt systems, with about 40 kilowatts going to the propulsion system. On our journey to Mars, we're going to need to start looking at larger systems, 200 to maybe 500 kilowatts, to be able to deploy the supplies that we need, and potentially be part of a crew propulsion system too. You can use it in a hybrid mode. As I mentioned, the robotics segment, you've got a couple pictures. This is a prototype of the CRS that's being developed down at Langley, the 7 degree of freedom robotic arms that are being developed at Goddard, and the microspines being developed at Jet Propulsion Laboratory. This is kind of the integrated prototype up at Goddard. I'm fond of saying that the time that the technologies and the capabilities that we have on the Asteroid Redirect mission are not mission unique. They can be applied to a wide variety of missions, in particular on the journey to Mars. So the last slide shows a notional Martian moon crewed exploration vehicle, and what it demonstrates, and I don't know if folks can completely see that in the back, but in this concept there are 6 of the CRS limbs and the robotic arms and grippers that are being used. These grippers can be used for things like boulder collection. They can also be used to climb cliff walls and lava tubes in both robotic in a robotics setting. They can also be used as a zero-G anchor for drilling with crew members. So there's a lot of applications, and what we're going to do on the Asteroid Redirect mission is kind of take that first hop off the surface of a low-gravity body. Hopping is a very effective locomotive mode on low-gravity bodies, and we're going to demonstrate that mechanically with the arm system. On an explorer like this, you would hop off the surface of Phobos or Deimos, gain an altitude, use thrusters to propel you, push you back down, and literally explore the surface through that hopping motion. So with that, I'd like to thank you and for your time and attention tonight, and ask if you have any questions. Okay. I think you had your hand back there.
This might be a silly question. Is there any risk that by using this gravity tractor beam that you could turn this NEA into a PHA?
Yeah, so 2008 EV5 has no close approach that would cause a hazard, okay? We are deflecting it by a very minuscule amount. We will do we haven't done all of the forward progression of the orbit, but right now the preliminary is that absolutely not. As a matter of fact, we have the choice of which way to pull the asteroid in the orbit, and we can actually put that very small delta V in a way that makes it even safer. So there's no issue with that as being a hazard. And that's one of the reasons for selecting that body. I think here we had your hand up, trying to go how they answer, raise their hands. Oh, there's a microphone.
Of course, you're looking for well-behaved asteroids that you can, the one you selected is going to be a well-behaved asteroid. There are some we've heard of that are not so well-behaved, that pairs of asteroids that may be gravitationally linked at a distance greater than their masses would suggest. Do you have any insight into that phenomena?
Are you talking about a binary system?
Yeah.
Yeah, certainly a certain percentage of asteroids are binaries. It is possible that 2008 EV5 was a binary at one point, but right now there's no indication with high-resolution radar, there's no indication of any moon with it, any moonlet. We would probably stay away from a binary system as a first mission, but there are actually some very interesting orbital dynamics that occur in a binary system that you actually could take advantage of. But the asteroids are varied in their size, shape, and how many companions they have. Right here.
Is there any reason why you haven't targeted an economically important asteroid like 2000 BM19, worth about $17 to $36 trillion, could fund NASA for the next 100 years? Is there a reason why you wouldn't go after such an economically viable target?
Yeah, it's timing is really it. I haven't looked at that particular target to know what the mass return, but each asteroid has what we call a synodic period, how often it becomes advantageous in terms of distance. Asteroids that are in very near Earth orbits have a very long synodic period because they orbit at almost the same rate, kind of like two race car drivers just, or if you've been out on the highway like I was today, not moving very fast with respect to each other. It takes a long time for them to come back around. Those are the best ones. We want the boulder to be back in cislunar space by 2026 so that we can incorporate it in the human exploration mission. It's very possible that we can use these technologies once we've tested them to go to another asteroid and bring back even more material at the right time. And so there's one target, 2000 SG344, which is unknown at this time, but if it's carbonaceous and has valuable resources on it, can have return masses of thousands of tons, and it comes along in the late 2020s. All the way in the back, sorry, making the microphone.
Right. Thank you. It's very interesting talk. On the benefits of the ARA mission, in your personal view, what is its biggest weakness?
Biggest weakness. You know, I think that there's always unknowns, and that's why we go out and explore. Our knowledge of asteroids is far from complete. Probably from a capture standpoint, the surface cohesion, how stuck is the boulder? We don't think that the cohesion will be very high. If it's higher than expected, then we'll have to figure out ways to pull the boulder off the surface. You know, the risk of the technology is proving out, again, it's a capability demonstration mission. We're going to test the electric propulsion system for longer than it's ever been tested in space. Ground tests are going on right now to minimize that risk, but there's always a risk there. There's a lot of things that could go wrong with the mission, but to be honest, the thing I'm most scared about is the launch, because you spend 10 years of your life working on this mission, designing and planning it, and if the launch doesn't go right, in a matter of minutes, the mission's done. So that's a risk that we have to take right now. I wish we didn't, but that's with rockets, that's the area that most concerns me. How about right here in the middle? Oh, hang on. Hold on, I'm sorry. And I got him, and then I'll come back to you real quick. Go ahead.
All right. What I'm thinking of is, say that there's a boulder you'd like, but it's stuck. Would you pick up, say, 2 or 3 smaller ones and substitute?
Yeah, so we're actually designing the system to be capable of picking up a 6-meter maximum extent boulder, so about 20 feet across. The 20 metric tons that we can bring back from 2008 EV5 won't let us exercise that full capability. Probably something in the order of 3.5 meters maximum extent. So something about as big as this table over here. If the cohesion turns out to be lower, we have multiple capture attempts. We have the system designed that it can come back up off the surface. We can reevaluate. If the cohesion is higher than we expected, then we would go for a smaller target. Our threshold is something, you know, larger than a meter or so, 1 to 2 meters. The cohesion falls off quite rapidly as the size goes down, and we think that we have a system that can handle a wide range. Okay, one last question here, and then we'll wrap it up and go to the debate.
Yeah, a question to the electric propulsion. I mean, there are 2 aspects, one for the asteroid mission, the other one for the Mars mission. For the Mars mission, if we are looking at the Mars mission scheme, which we have in mind, Mars direct, I don't see really the advantage. But for the redirect mission, is it the case that you only trust the electric propulsion because of its reliability and long life, or what is the advantage against chemical propulsion? Because the advantage physically is about 50% increase or something. I mean, the efficiency is not enormously higher.
Yeah, so the efficiency typically of advanced chemical rockets, liquid hydrogen, liquid oxygen is the best, is about 450 seconds of ISP. We're talking about systems in the neighborhood of 3,000 second ISP, 2,500 to 3,000 here. So you've got a factor of about 6 or 7 in the efficiency, which is actually the only way that we could do the asteroid redirect mission. We could not do it chemically. And when we start talking about pushing around large masses and infrastructure in the solar system, again, the SEP systems are going to be like the tugboats on the river. They're not fast, they're not glamorous, but they get the job done much more efficiently than chemical. For time-critical operations, certainly chemical rockets are important, and we are looking at hybrid solutions where we do high thrust to get out of the gravity well, then we accelerate very slowly with the electric systems, decelerate very slowly, and then fire thrusters in the Martian system when we arrive. So there's a variety of different approaches, but pre-deploying and moving around large masses in the solar system really needs the efficiency of SEP. I think that's it. So again, thank you very much.